Good morning, all of you. I welcome you all for the guest lecture on Quantum Leap in AI World, conducted by the Department of Physics, Savita Engineering College. And this is especially meant for the students of CSE department. And my hearty congratulations for the convener of the program and the chief guest. And let me introduce the chief guest through Ms. Savita. Let me invite Ms. Savita, madam, to give the introduction of the chief guest.
Yes, ma'am. Good morning, everyone. I'm profoundly delighted to take an opportunity to introduce our resource person, Mr. Rajesh Bhaskaran, for today's guest lecture. Mr. Rajesh has completed his engineering graduation in Nagpur University. He has more than 15 years of experience in ICT industry that focused on problem solving and driving business outcome. Mr. Rajesh is a certified cloud professional who worked across different sectors of IT, from telecom, banking to government departments. Currently, he is working as Director for Enterprise Architecture Practice, Transport for New South Wales, Australia. Thank you.
Thank you, Savita ma'am. Now I request Mr. Rajesh Bhaskaran to address the gathering and cast the light of his knowledge upon the students' community.
Thank you, Savita ma'am and Sangeeta ma'am, for this opportunity.
Thank you,
my
sir.
name is Rajesh.
Thank you.
It's all right. My name is Rajesh Bhaskaran. I think thanks for the lovely intro. When you hear it like that, it is overwhelming, but it's a this course. I'd like to talk about the course structure a bit. You know, the short 1 hour. The subject we are covering is AI, quantum, especially quantum in quantum realm, right? Quantum leap in AI. So the way I structure it is, I cover the horizontals because it's almost impossible for us to cover the different verticals within the given time frame, and it is not justice to you people to explain all the concepts for first year students. So the way I structured it is, I'd like to start on a funny note. Like Nityananda says, I've covered the breadth of the quantum, not the depth of the quantum. So just to give you more coverage of the topics, the various set of topics that are available in AI and quantum realm. Let me share my screen and then let's get right into it. So I'd like this to be interactive, if you guys don't mind. I hope we have a question and answer session at the end. I'll throw a few questions through the chat window, see if you can answer. If not, I'm always here. And you throw a few questions back at me. If I'm able to answer, that's fine. If not, I'll take the questions on notice and I will get back to you with answers. Can you see my screen? Okay,
Yes, sir.
Get right into it.
Yes, sir.
All right. Quantum leap in AI world. I covered the course title. So what is an AI? It's an interesting question. So AI is a buzzword across everywhere. So everywhere I go, people want to know more about artificial intelligence. So artificial intelligence, to put it in a layman's term, this is what I use. It is anything that mimics human intelligence. That's what is artificial intelligence. Anything a human possesses, you make a machine do it. That's artificial intelligence. So this is a busy slide, but I'll try to go in detail in a very slow manner. So as you can see, within the artificial intelligence, and before I get into the artificial intelligence, so the way I'm going to cover this is, I'd like you guys to first understand artificial intelligence and the complexities in artificial intelligence and the way things are done. And I also want to cover it in a more pragmatic way, so you guys understand what it takes to deliver an artificial intelligence platform in the real world. Only then you would be able to appreciate the complexities that are there in artificial intelligence world that are overcome by quantum computing and few other concepts. So hence why the course would talk about this seminar. In the seminar, this particular topic, I would cover mostly artificial intelligence, and towards the end, when it all makes sense, I'll open out quantum computing and we will dig slightly deeper into quantum computing. Okay, so coming back to artificial intelligence, as you can see, so it is, as Frank Chen said, it's artificial intelligence, a set of algorithms and intelligence that try to mimic human intelligence. So what is machine learning? So machine learning is a sect, or it is a subdivision within artificial intelligence. That is, ability of the computer to learn and correct itself with the data that it's exposed to. For example, if you are looking at, a machine learning algorithm is learning how to, process a particular image, let's say how to identify a face. So it automatically, so once you set the facial recognition algorithm, it automatically, learns and it automatically improves the accuracy. So that's what is machine learning. We'll cover all that in detail. And the next set within that is deep learning. So deep learning is an extension of machine learning, but it is exactly, it's like exactly mimicking your cognitive brain functions, like your vision, your hearing, and your speech. All these things form, deep learning. So the research into those areas and to make computers do these type of functions are deep learning. And to underpin all these things, right, the basis of all this is data. So if you don't have any data, you cannot get the machines to learn anything. So it takes quite a bit of data curation, and it takes quite a bit of data science. You have to mine a raw set of data that you collect. I'll cover that in detail when we go, but this is just an introduction. That's it. So exactly as I said, so within machine learning, we have three types of learning that are available: supervised learning, unsupervised learning, and semi-supervised learning. So the whole world that is built around us, the AI world, uses these techniques, these concepts. Can anyone think of any sort of real world application of AI that we are using every day in our day-to-day life? Okay, if you can't think of anything, I can quickly tell you. Electronic cars, it revolutionized the AI world. Tesla, the autonomous car, so that uses computer vision, which is a combination of supervised learning and unsupervised learning. What it basically does, I'd like to cover this supervised learning. So the supervised learning is basically, you teach a computer how to identify an apple with its features. You say apple would be red in color, it's got a round shape, and it's got a pointy tip at the top of it, and all the sort of things. This is called feature engineering, which we'll cover at a later stage. But basically, you're teaching a computer how to identify an apple. That is what is supervised learning. So if you see, you have a training data set with images that has got different colors and different angles of apples that you expose the computer to, the machine learning model to, and it then looks at it, and then you have to label it saying this is an apple, and then it reads the label, and then it identifies the pattern. And when you input a raw data after you train the data set, then it can distinctly identify what's an apple and what's a mango and what's a pear. So natural language processing is a good example. Natural language processing is voice to text, text to speech, all these linguistic use cases where you teach a machine how to speak a language. There's a lot of nuances that goes into constructing a language, right? It's not like English has got grammar, and Tamil has got grammar, and all these other languages have their own grammar. But what makes it complicated is the dialects. Within Tamil Nadu itself, just to localize the example, within Tamil Nadu, you have the language has got different dialects every 200 kilometers you travel, right? The dialects as in the slang, the way they talk Tamil. So when a computer, how do you teach this to a computer, right? it's hard. The computer cannot understand a guy who speaks American English versus the guy who speaks in Australian English versus the guy who speaks UK English. They're completely different. The terminologies are different. The way they use the words, the sentences and the words are completely different. So this is where unsupervised learning comes into picture. So once you teach a language, once you teach a machine learning model, once you supervise it and teach it how to read a language, then you expose it to your Shakespeare's and your Webster's and your dictionaries and all those sort of things. And it then clusters the results, and it then, infers, and it forms its own opinion, and then it starts adding value. That's what is unsupervised learning. Again, so getting back into deep learning. So I'd like to give a distinct example, right? So for us to relate to deep learning, this is the core of all the artificial intelligence that's happening around us. So a good example would be, you imagine, so you yourself imagine you have two eyes, and then you have a visual cortex at the back, and then you have neurons that's running back and forth between yourself, your virtual cortex and the brain. So that's basically what a computer vision is. A computer vision will have a pair of cameras that's looking at an image or live streaming into a scene. And then what happens is when it goes in, and your neurons are your algorithm machine learning models, and then it goes into, through the power of GPU, it processes information. So this is the real neuron to your left. You can see there's a nucleus, there's a cell body. Of course, this is not a biology class, I can't tell you much, but you look at to your right, you have artificial neurons. So this is what is the core, like the atom of the machine learning, the algorithm. So this is where all the processing, all the computation happens for the machine learning model. So this is basically your artificial neuron. So if you relate that to how your neuron would help you deduce things, like when you see an object for the first time, you don't know what it is. Like a human, when you see something new that you've not seen before, you're inquisitive, you want to learn. Unless someone tells you what that is, you would not know what that is. It's exactly same it's exactly the same situation with computer vision. So when you use a machine learning model through computer vision to watch an object, you got to tell it what it is: a mug, a bat, or a gun, or whatever. So that's what people do, and that's what is called training the machine learning model with the available data set. And that's why training becomes important. So you had the luxury of learning as a kid from childhood. You had that accumulated knowledge. Now you know everything. Whereas when you start a machine learning model, it starts from ground zero, and then you have to expose it to the right set of data. You have to be very careful there as well in what type of data you expose. There's a lot of other considerations like bias, ethics, and all those sort of things, which we can cover at a later stage. So you saw the artificial neuron. This is the artificial neural network. So this is a set of architecture. What this is this makes use of, the deep learning. This is the crux of the deep learning. So it uses a specific architecture to process information in a fragmented way, but at the same time, it does a lot of parallel processing and a lot of permutation and combination and probabilistic values to deduce a particular value. And for example, an apple would go through, some might think it's apple, some might think it's orange. So all those possibilities would come, and at the end of the day, it is the probability. So it would say 70%, if the quality is really good, the image quality and the data quality is good, it would almost 100% identify. But if it's not clear, if it's not a very clear image, then the accuracy reduces. Okay, so that's the boring bit about artificial intelligence. That's the theory. So you know what is an artificial intelligence now. You know what machine learning is now, kind of at a high level, and you know what deep learning is, and what are the concepts behind it. So what are the real use cases? How do you deploy? In the real world scenario around us, how do we use this? So for example, in a business transaction, like you're doing a banking transaction, these days, everybody uses mobile phones, right? So AI is, pervasive action during the business transaction. You use fraud detection. So the artificial intelligence fraud detection model detects any unruly type of request, and it flags it. And in a business entity, it considers, it's a risk-based assessment. So if you input a lot of risk parameters into the artificial intelligence and machine learning model, and it classifies whether you're a person who's most likely to pay the debt back or not. And there's a lot of other event streaming use cases and, you know, AI Edge. So the AI Edge is the evolving technology. I think with Google's next version, Tensor, they have, you know, a powerful chip that can do, you know, AI Edge using your phone. So your phone is much more capable than your laptop these days. Whatever phone you're getting, it comes with a lot of, it comes packed with a lot of compute power. So this is what this is my experience. I'd like to share my experience with you know, implementing a pragmatic way of implementing an artificial intelligence. So when I started, you know, 3 years back in New South Wales Police, it's like it's comparable to in Tamil Nadu Police as well. You know, they have CCTV footages. You know, they have a lot of information and, you know, a lot of files coming from different areas through an investigation, for an investigation. And in New South Wales Police, it takes 10 people on an average to go through 10,000 hours of CCTV footage to investigate a homicide case. A homicide case is typically a murder case or something like that. So for them to look through the video, it takes close to, you know, like, you know, a lot of time and 2 years to complete an investigation. This is a very big pain point. This was a very big pain point for New South Wales Police. So when I joined the team, I evaluated a lot of platforms, you know, machine learning platforms, and we completed some sort of a requirements session. And then we realized, okay, this is what we need to do. And then we stood up a foundational AI capability for them, which they call Insights, which goes through the CCTV footage, 10,000 hours of CCTV footage, which would take normal people to go through 6 to 8 months. It did it in 15 hours. So that is the type of efficiency that we're looking at. So in terms of, you know, abduction, in terms of murder and all those things, the first 24 to 48 hours is called the golden hour. That's when you need to identify the criminals through these evidence that you get, right? If you identify after 6 months, the criminal is by then he's gone. So this gives you that, you know, ability to trap and catch criminals at the right time. So these are some of the use cases that, you know, I have evaluated in law enforcement in particular. Threat detection. Threat detection is you have a live CCTV footage watching in a public area, and if somebody is, you know, behaving violently, or if they are doing some sort of a, you know, knife or sort of a thing they're carrying, it's a threat detection. You know, number plate recognition, which I'll cover in detail, language translation, and so many other things that we evaluated. So this is how you approach a problem. This is common. This is consistent across. You guys are computer science engineers. I think you guys should start to think logically. How do you approach a problem, right? So this is what it is like. You have a problem team. You have a solution team. The problem team first understands what the problem is. It all starts, any IT project starts with a problem statement. I have this, I don't have this, something like that. I want this or something like that. And it goes into analyzing the process behind implementing that. And then same with machine learning model, you do a model processing, and then you understand the data that you're dealing with, and then you prepare the data. And once you have the data and the understanding, you go about developing a machine learning model, and then you release, and then once you release it, you automate it. This is a basic AI adoption journey. When you start, it's very expensive. It's not a cheap process to run. So artificial intelligence takes, runs on a very high compute, which is called a GPU, which GPU-based infrastructure, which is a graphical processing unit. It's not CPU. It takes a GPU to run, chew up all the data. If it's for a trial, we can probably get away with CPU. But if it's for a real use case, to read through a lot of CCTV footages and images, you need GPUs. And we used NVIDIA DGX, GX100, which is one of the powerful, GPU computers or artificial intelligence computers available at that point in time. It's kind of a supercomputer. It's got 64 cores, and it's got close to 12 GPU cores as well, which is very powerful. So this is a typical activity in an ML engagement. So when we go down the path of implementing a machine learning process, what is a use case? What is a use case? A use case is any sort of a problem that you're trying to solve. For example, if I want to automate, if I want to convert my voice to text, that is a use case. So to build up a use case, it is usually 2 to 5 days to understand what type of data we're dealing with, what audio and all those things. And most important thing in artificial intelligence and making it really possible is the feasibility study. So when you take up any process, and this is applicable in real world projects as well, you find out what your use case is and you do a feasibility study of whether your idea and your thinking process is really feasible. As a proof of concept, when you run it, you will definitely find out whether it is feasible or not. And then you go on to release something called a minimum viable model. That is, a minimum viable model is something with a minimal set of features, but it's something that helps you realize the business benefit as quick as possible. So these are different techniques in machine learning, deep learning decisions, clustering analysis, representation learning, unstructured learning. These are at a different layers of the application. As you can see, at the topmost layer, you have a rule-based machine learning engine that is deep learning decision making, and the cluster analysis is more for a data visualization use case. And then, representation of learning is through data integration, and then, exposing it out through chatbots, and other areas. Or this is the consumption channel if you look from downward to up. So any idea, as I said, just thought to give you guys into an IT, if you turn into an IT engineer, if you become a software engineer or an ML engineer, this is what the thing in the center, the black thing, the business hypothesis, it all starts with that. But that's your mind map. Those are the steps that you have to take to implement a project, right? So those are different stages that you have to go through, you have to tick off. So it's not an easy process like you saw it and then you did it. It's not as easy. You need to plan it. There's a lot of planning that goes behind a machine learning, building a machine learning algorithm or a project per se. Let's get to the architecture. So what is an architecture? I'm sure you guys are first year. I'm not sure whether you guys understand IT architecture or the benefits behind it. I'll usually give a town planner's analogy. Like if you have a new city, you have to plan a town, you are doing a planning, and you have to decide, where a shopping center is going to come, where you'd have, highway arteries of roads, and where you'd have, your sewers, and where you'd have, cinema halls and all those sort of things. So IT architecture is very similar. You would have myriad of applications that are running parallelly. So you have to architect it in a way that it all works cohesively together to deliver a common output. In here, you can see this is a data lifecycle, right? You acquire the data through different sources. I hope you guys know what a structured, semi-structured, unstructured, streaming data means. I'll quickly tell you. So structured database is a record that you find in a database like Oracle, SQL, any record, you take it as a structured information because you can query on it easily. Semi-structured is your JSON, your XML files, all those sort of, your information exchange mechanisms. They are all semi-structured as an example. Unstructured is your images, your video files, so on and so forth. And streaming data is, a real-time data, streaming of real-time information back into the system. And these are all the roles that it takes to build a machine learning model. You need a data scientist to look at these information that you're collecting collectively into a logical warehouse, data warehouse environment, and they look at the trends and patterns. For example, Facebook does that a lot. So if you go to your Facebook and you browse using your Google browser and you go to some shopping site, and then you come back to Facebook, you see that shopping site in your Facebook. How do they do that? It is something very similar. They do a lot of mining using your own browser analytics. They take all the data and then they populate it. But this is what it takes. This is what happens behind the scene, and this is what they do. So in the middle is your engine, is your warehouse, and your machine learning model that does all the processing and that does all the training. And at the edge towards your right is where you actually see them. The users, when you use your Facebook apps and things like that, that's where you see that output coming. But there's a lot of processing that happens at the back end because it needs a lot of compute power. I'll pause for a minute. Do you guys have any questions now? Can you hear me?
Yes, students, if you have any questions, till now you can ask. For any clarifications, you can ask, sir.
That's fine. You guys are a shy mob. That's fine.
I think, yes, you can continue,
It's-
sir.
When you watch I promise you, when you watch the video, it will all make sense. This is a painful slide that you have to go through for you to understand. You may not appreciate this now, but I'd like to cover as much as possible so you guys understand and appreciate what it takes to develop an artificial intelligence model, right? So look at this. So this is what, it's a simplistic layman term, in English, I just tried to do it. So when you from a data engineer, there would be a data engineer in a real world who would pump through applications and through, different sources of data. They would be pumping data through different channels, and data ingestion means ingesting means you're digesting. So you absorb the data through integration channel. And then once you get, for example, I get data from your browser, I get data from, your phone, I get data from, your shopping history, I get data from, your banks and stuff. So I start to form a profile, and then I cleanse and I curate. This then goes into a data preparation channel where you prepare the data, and feature engineering is one of the key aspects of a machine learning model. So this is what defines what your outcome is going to be. So for example, you want to identify a fraud detection model. So you have to tell what are the key features of, or what are the basic characteristics of a fraud detection payload. For example, or how do I put this in a simple terms? So for example, if you have to identify a car through a facial recognition, the feature engineering is key. So you have to tell the machine learning model what are the basic characteristics of a car. It is rectangular in shape to start with, and then you start to reduce and add geometrical vectors into the equation, into the feature engineering. So choosing these geometrical vectors, it would, in an image, which will have myriad of things, traffic lights, blah, 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 it would identify a car. So that feature engineering is very important. And then your hypertuning parameter as well, of how much you're willing to compromise on the quality and, and what false positives and things like that, that spits out a candidate model, and then that goes into your behind your application. So this is a basic landscape of a machine learning model. So from a data on the top, it turns into a actionable output or an actionable insight. By insight, I mean a meaningful data for you by the time it comes out of the machine learning model. Let's see this. This is my architecture. So we're all talking about number plate recognition. So in Western world, I'm not sure about Chennai or Tamil Nadu. Maybe it's not there yet, but I know they are working. This is a very key automation, and it is very, very important in averting a lot of unruly driving behavior. So just to bring in discipline into driving, you see a person violating through a traffic camera, you can send fines straight away to them, right, straight to their home. So this number plate recognition model is very important in achieving that. So what it takes to identify a number plate from a car in a traffic light, you guys have to ask yourself, right? Sometimes, how do they identify it's my number? It is not at all manual, at least in this side of the world. It is not manual, because in a day, you see so many people crossing and you take so many pictures. It is almost humanly impossible for anyone to sit and identify number plate by looking at the image. So this is all automated these days. And the way it happens is, if you look at the first left-hand corner, there's a camera feed box. So a camera feed comes in. And from that image where you have traffic light and everything, a car detection model is built. A car detection model is a model that identifies a car from a picture, a group of like images, a group of objects that are there in the car, in the canvas of the image. It identifies cars. It identifies 1, 2, 3, whatever number of cars there are, and then it crops the vehicle that is in question. And then once it crops the vehicle, it is very important for you to do the make and model. Now you might be curious why make and model, right? So make and model is important purely because you need to identify the length, the height, and the configuration of the car. Where would the number plate be? If it's a SUV, the number plate would be higher up. Whereas if it's a car that's got a low bed, the number plate would be much lower. So you need to identify what make and model is. There is an algorithm behind that, and you would have a vehicle data system that is associated with that. So once you identify the number, make and model, and then there's a cropping that needs to happen at the right number plate. So once the number plate is cropped, then you then pass that through OCR. OCR is optical character recognition. It is looking at the image. It's an older technology. It existed even before AI was there. It was a computer would look at an image and read the numbers. So that OCR runs through it, and then it spits out a number plate. So in this itself, the number plate recognition use case itself, you use 3 or 4 ML models. You use 4 models. So this is how the real world would be. So you would have to use these machine learning models in combination to achieve one single output. So you had a car detection algorithm, you had a make and model identifier, you also had an OCR to identify a number plate. I'll show you a GIF or GIF file. You see, this is a GIF file. This is how computer sees it. If you look at it closely, you see to the left-hand side, this is how OCR happens. You have a raw data, that is coming in from 0 to 9. The computer looks at it like that. To it doesn't make sense, right? For example, as an example, I ran through number 7, so we can easily relate. At the top is the input. It crops the individual numbers, and then it tries to see, for example, what are the characters. This is where your feature engineering, as I said, your feature engineering is key. How does a computer identifies number 7? It's got pointy edges. And it's got a curvy line, and it's got and also a straight line at the top, and it doesn't have any soft edges. But if you look at the softmax layer, this is the neural net basically. So this is what I called previously as a neural network. This is a convolutional neural network, which is one of the architecture patterns that is used for machine learning. It is very popular in computer vision use cases. But if you see at the first iteration, it's a number 7. But if you look at the softmax layer, the brighter the white light is, the more confident it is. So machine learning model never accurately tells you it is number 7. It tells you it could be a number 1 because it's got a straight line. If you look at number 1 also got a vertical line, right? So that's why it thinks it could be a 1. And it thinks it could be number 4. It's probably because it's got a slanting line like a 4. The 7, the horizontal, the vertical line in the 7 looks more like a number 4. So it thinks it could be a 4. And it thinks it's a 7 because, and if you look at it, it is brighter at number 7 because it knows it's got all the characteristics of, a straight line and a slanting straight line, which is more of a characteristics of a 7. So if you look at it, it's got some sort of a bright light near number 9 as well, because it looks very similar. So that's how a real world machine learning model deduces or predicts based on the data input. So it gives you a probability. It says 70% in this, it says 75% I believe it's number 7, and it also says 20% I believe maybe a 9, and maybe 10% it's a 1. That's what it gives. And then from there, through that, you have to do a lot of training to perfect it, to improve it, and then you have to shape it up in a way that it's bright 7, right? It just glows in 7. So this is the real use case of this is how a machine learning model or a computer vision sees every input, and this is how it deduces at each layer and finally outputs what it believes. FC is fully connected layer, where it collates all the different neural network inputs and then finally gives its output. Any questions here? Oh, I see a lot of chat. Okay, that's fine. We can continue. If you have any questions, you can save it as well, and you can ask me towards the end. So very similar use case. let's say you get a call, every time you make when a banking professional calls, she says it is recorded for quality and training purposes. This is nothing but a quality exercise. Let's say if you call Amazon or Google or any other company for buying phones, their phones like Pixels or whatever, this is exactly what they use behind the scenes. So what happens is an operator takes your call, and then they collect, they ingest, and all those sort of things that I showed you in the previous slide. How an ingestion takes place. It gets ingested, and the audio file gets split. Your audio file, that your conversation with the operator or the customer service executive, and your conversation, that audio file gets split into a number of wave files. That is called a channel split, and then it gets enriched. And then what happens is it goes through a neural network, NLP, and then it does. Sorry, you have any questions? Okay, I'll continue. Then from signal enriching, it converts that audio into speech to text. So what happens is it converts all the audio into a transcript file. So it automatically translates all the information. So this is what happens even when you, in your new phone, if you're using Android, if you enable transcription, or if you enable transcript service in near your volume button, you would see it. It's a feature. When you speak, it automatically translates or transcripts your audio into text. This is what happens behind the scene. So it channel splits it, it enriches it, and it goes through. It runs through neural nets, and then it gets a speech output, and then that's what you're left. You have something called a transcript that then goes through natural language processing. With goes through several set of your quality control mechanisms. For example, if you want to measure a quality call, how well you responded to a customer, you have to add all those features in this area. This will determine whether you've appropriately answered and whether you've done your job as a customer service executive through this linguistic features and heuristic rules. So heuristic rules means basically your normal programming. If this, then that, for, and all those sort of normal, your mundane programming and your Java programming, that is heuristic features. So once it goes through that, then it makes a recommendation saying this particular call you don't have to review, this particular call you have to review. So out of, let's say, 15,000-20,000 calls, audio files that you record in a day, it only flags let's say 50-60 calls that are exceptions, that are not good, that are bad, that had a very quiet that had quite a bad customer service support. So it is governance by exception. So what happens is you are only watching files that are bad. You're not going through the whole lot of files, or you're not using some sort of a random audit. This is more accurate. So this is what Google and all these Amazons and Googles and all these guys behind the scenes, this is what they use, and this is what we leverage as well. This improves a lot of process efficiencies and man time. Similar to media monitoring, this is a very important topic. Why I am choosing all these things is you guys are in your year 1. By the time you come to, let's say, year 4 in your engineering, these topics, these systems and these softwares will will rule the market. This is the industry trend. These are the things that are going to dominate at least the Indian markets in the coming years, and that's why I chose these things, and I'm choosing to show you how it works. So media monitoring. So what is the power of social media? We all know. I'm not sure whether you guys know Black Lives Matters. It created quite a lot of protest, and it made a lot of governments struggle, because most of the protests were organized through social media. So you have a Facebook group, people organize, and they come as a mob, and then they do some sort of a protest or some sort of issue to or nuisance to public. They do some sort of protest all of a sudden, and there's no way of tracking. So media monitoring, what this software does is, it through Facebook, Instagram, there is a media consolidation platform that is there. I don't want to cover that, it's out of topic. I can, but it's a tough subject in itself. But what happens is you can monitor a radicalized individual. For example, some identities in India, they are popular, but at the same time they're creating a lot of negative sentiments. You can using these algorithms, you can monitor them, and you can look for keywords like protests, bombs, or whatever, hijack or abduction, what sort of things. And you don't have to manually do it. For a police officer or for any sort of a government agency to manually do this, it will take a lot of manpower and subject to human error. So what this does is it watches for keywords, it brings in stream of data from different sources, and it monitors radicalized individuals. And then it monitors how they are affecting a particular post. For example, if there is a, I don't know, maybe controversial topic, but NEET or whatever, if there is a topic like that, how a particular individual is affecting that particular opinion amongst the public. So those kind of things can be tracked, and those kind of things can be monitored as well. It is very important. Again, if you see, as I previously showed you, it goes through a speech recognition, goes through Gaussian processing, from there text, and then NLP, and then it flags with a recommendation or no recommendation. The base architecture behind this is common, but with slight variations of machine learning model. Now, my friend, this is my friend. I took a picture of my friend through an edge camera. This is how a computer vision initially sees. The way deep learning works is it first identifies a person. There is something called a person detection model. It identifies from the picture. There is a furniture. There is a flower vase, and there is a person. First, it identifies the person, and then in the person it identifies the face. So we ran into trouble. We cannot store people's face because of privacy issues. So what we did is we managed to extract facial vectors. You see those points, in the image, in the key points and posture detection. You see how computer measures the eyes, the distance between the eyes and the nose, and your facial vectors gets measured, and that's what gets stored in the database. So that's what is behind facial recognition. It won't compare pixels to pixel to match your face, right? That would not be accurate. If the image quality is bad, if you just have your structure, bone structure, it can still identify. This is how it does it. It just decomposes your face into facial vectors, into matrices, multi-dimensional matrices, and then it stores it in there. Imagine like a multi-dimensional matrices with a lot of dimensions. It adds it X, Y, Z, and then it stores it in the database. And when it comes to facial comparison, facial detection through a live feed of camera, this is what it does. It uses the facial vectors to identify, faces that are, in the photos. Again, this is, I don't know whether this is appropriate, but it's a bit too much. But this is what the world is moving towards. AI at the edge, in your watch, in your phone, in areas where you need mobile in a remote area. And there's a lot of use cases like this, like in your camera, for example, if I have a use case, good example is Tesla. If you look at Tesla uses one GPU and uses a computer vision at the front, and it does AI at the edge. If you look at it, it helps you navigate. So it uses it uses navigational system, which is also built on AI, finds the shortest route. Google Maps you use, that uses AI as well. So it uses all the traffic information, it uses all the geospatial information to give you the shortest route. That is also an advancement of AI. So this is what is the AI at the edge. Again, just to sum it up, there are a lot of things that are there in AI. Some are less mature, some are more mature. Less mature things, by less mature, I mean, if you explore that, you would not get much out of that. These are things in progress. These are developing. These are features that are being worked by the Googles, the Amazons, the Microsofts, and all these the big players in the market. So they're still exploring these ones. If you venture into that, of course, you will have a lot of open source models that gives you this machine learning models, but you would go nowhere. You would not be able to achieve real practical application because you would not have a proper data set to train these machine learning models. And if you're right, would be your more mature models that are your off the shelf. It's available in the market. If you log into Google, they offer, for example, Google offers speech to text. If you go into their cloud computing, they offer natural language processing, they offer computer vision, they offer number plate recognition and few other things as a service because it's more mature it's standardized. Just a minute. Sorry, that's my daughter. Moving on. As I spoke before, so these are some of the machine learning models that you can leverage from the market, different types of machine learning models that are available. You have the off-the-shelf models for simple speech recognition models. So you don't have to go build everything on your own. These are things that are available off the shelf from cloud providers like Google, Amazon, Microsoft. They all have similar features depending on your costing and your hosting type of use cases. You would choose which model to go with. Some also comes to bring your own data. So if you have to, for example, you have to detect a machine learning model on how to detect a gun. That's a very niche use case, which you will not identify, except in law enforcement area. You will not have many other use cases across the industry. So it's not yet there. So you have to bring your own data. You have to do your own training. You have to be very specific with your data. And then, of course, hardware accelerations are done using GPUs. TPUs is a tensor processing unit, which is very special to Google. Google offers TPU, and then FGPA is a field gate processing, which is at the edge, AI at the edge. If you have a facial recognition type of a machine learning model, you can burn it in the chip and you can attach it to a camera and it will identify faces. So FPGA is used for those type of processing use cases. So these are the open source tools that are available in the market. So you guys are young. You should not wait for for your job or your workplace to teach you how to do your machine learning model. You can build your own hello world using these type of open source models. You have PyTorch, you have TensorFlow. You can create your own test accounts in Google, and then you can trial all these products out. By trialing these out, you can perfect. And you can get better at it. So you can see it's easy to use, it's more open source. Flexibility is when you use more, when you go more platform. So this is a simple, before I wind up AI development, right? I just would like to give you guys how you approach an AI project or a software project, just briefly. So you would have an ideation phase of, that means what is possible. And then you have a feasibility phase of what is feasible. And you have a pilot phase on how does it perform, and then you have an operation phase where you deploy it. The reason why this is important for any AI model is because it's exploratory. You don't know, AI is still exploratory. By exploratory, I mean, you don't know whether you would be achieving the business outcome unless you do some sort of a trialing. Hence why this is very important. As I said, ideation phase, even if you approach a project, your uni project, university project, you go through an ideation phase where you jot down, list down all the creative ideas for a machine learning model or an IT project, you list it down. AI is not different, it's the same phase. You consider so many other parameters, which I don't have to cover. Feasibility study of, is it possible? Would it fail? And all those sort of things. You had an idea of building a car. This is the feasibility study. For example, what are the ethical parameters, what are the infrastructure parameters that would stop your projects and all those sort of things. And pilot is when you really put it out to a small user group to test your idea. To a small user group, you expose and just get it to test. And then through that, you get a lot of feedback. Every machine learning model is attached to something called a feedback loop. So every time it makes a mistake, it learns. So which is why piloting a machine learning model is very important, because through piloting, you can avoid a lot of errors and you can gather a lot of learnings. That's why when they release a chatbot or anything, they say, oh, I'm on my training wheels, I'm still learning, blah, blah, blah. That's probably because it is still learning and it is still in the pilot phase. And then operation, there you go. You have a fully functional car. So I'd like to quickly show you what I have, delivered in New South Wales Police. I'll share an audio file here, a quick video file for you to understand. So all the concepts that I mentioned to you guys, I've used it here. So if you look at it, this is the final product that I delivered for police. Can you guys hear? Hello, வரலையா வாய்ஸ்?
Sir, in the mode option, you can have an option share audio, share sound, sir. Just click that option. Just more option, you can able to have option share sound. Is it audible now, sir? It is audible, sir.
Sites. Discover the power of artificial intelligence to uncover your digital data for investigation. As an investigator, I have spent countless hours viewing videos manually. Now, introducing Insight's platform. With easy-to-use functionality for all levels of user. You can now view your files and analyze in different types of analytics to assist your investigation. The first job I want to do is to extract all the faces from this video. This will help me save time in reviewing the footage. Here, you can see all the faces extracted from that video. Further to this, you can save the results, bookmark, and view the video in which the face has appeared from. Now I have an image of an unknown suspect and want to find out if he will appear in my analytics. This feature allows me to identify when and where the person appears in this video in a short period of time. But what if I don't have a clear image of the face? I can also identify the person when the clear faces aren't available. I can track the same person across multiple footage to help identify the movement of this person. Vehicle recognition has helped me cruise through the footage in a time-efficient manner. Insights have the ability to recognize the color, the make, the shape of the vehicle. Once my videos have been analyzed, I can combine and stitch the footage into one video. Here's the sample of how I stitch my footage. I can crop the footage, redact important information, trim the clip, adjust the speed and volume, or view the details of this footage. Thank you for joining me in this journey. I cannot wait for more features to launch. We are working towards features such as advanced filter and search, speech-to-text transcription,
Can everybody hear me? I think you can hear me now. Can everybody hear me and see my screen?
Yes, now
Yes,
it is
sir.
audible.
Okay, sorry. I think Zoom, I'm never a fan of Zoom, and my official office laptop, it just blocks Zoom. So that is the real use case. It really, we delivered an artificial intelligence for New South Wales Police Force, and they are now able to catch criminals at much faster pace. So this is making difference. A software like this makes a difference, and even if it saves 1 or 2 lives by using this particular software, it is definitely worth the effort. It took us some time to deliver this, but now it is fully operational. And, I just wanted to show you guys. So artificial intelligence in its real world use would look like this. This is how it looks. So that's why I got permission from my previous agency to play this video to you guys. So you guys can actually see how AI makes a difference. Now, coming back to the presentation. So what is the challenge now? So we have delivered the AI projects, and then we started accumulating a lot of hours and hours of CCTV footages and images, and a lot of workloads, parallel processings, and the clustering, and all those concepts started taking shape. And where we fell short is, the classical computing. It was hard for us to solve problems using classical computing because we've almost reached the limit. And it got to a point where it's getting very expensive, and you have to stand up a lot of horizontal scaling, and even still some of the algorithms are nearly not possible. For example, neuromorphic cognitive models, adaptive machine learning. So adaptive machine learning, for example, is a very new concept. What it does is, like, when a bird, when a bird's young one is born, a bird does not teach that one to fly, right? It automatically learns to fly. So we are now looking at those type of behaviors, inherent behaviors, instinctive behaviors of animals, and we're trying to mimic the same thing in AI models. That the reason why we're doing this is to minimize the data training. So if you have a model that is architecturally more inclined to perform a particular function, then it is more efficient rather than training it through hours and hours of videos, audio, and tagging and labeling. It is a very tedious process, and there's a team that works behind this data mining team in labeling data and tagging data for the computer machine learning model to run through and train. So this is where we have quantum computing coming into picture. So quantum computing, let's jump into it. A brief history of quantum start. So quantum computing, before I start, you have to apologize. I have to apologize because it's a very, very difficult topic, and it is a very difficult topic and a complex topic to explain, but I will try my best. I put these things together from I'm doing a paper on this one, so I'm sharing my know-how with you guys, whatever I've gathered so far and my understanding and how I am using in my office. Unfortunately, I cannot disclose. What's happening is everybody is in this quantum race. They want to, be the first to identify, and even my agency is doing the same thing. So brief history of quantum. It started, as you can see, Max Planck. Everybody knows what's a Planck's constant. He started that, it all started with him. E is equal to hv. And we have Louis de Broglie. Anyone tell me what Louis de Broglie found? So he is the one who found a particle can behave both like a wave and, an atom can behave, a photon can behave both like a wave and a particle. It exhibits both, duality. So this is the guy who invented that. And then Erwin Schrödinger, Erwin Schrödinger contributed a lot on how the different stages of electron, gets affected due to, the ripple effects. But just a question, how many of you know what is a Schrödinger's cat? There is an analogy that people use called it's a Schrödinger's cat. You guys know what is a Schrödinger's cat? Right, if you know what Schrödinger's cat is. What, Danush, tell me what is a Schrödinger's cat? Okay, no problem. I'll tell you what a Schrödinger's cat is. I'll tell it in your terminology, right? For example, God forbid, for example, you've given your physics exam and you've not done it well, and you don't know, and you've done it to the level that you may pass or you may not pass, right? So funnily put, that is your Schrödinger's cat. You don't know whether the teacher is going to, your teacher is going to make you pass or she's going to fail you. Your state at which you're there of not knowing the outcome, but you kind of know that you've not done well, is the Schrödinger's cat situation. It's a funny analogy. I thought I'd share with you guys. But anyway, so it started with Werner Heisenberg, right? So Werner Heisenberg is one of the key guy who made that push into quantum realm. So it's usually counted from 1920. From then to now, it's 100 years. It's 100 years of evolution in terms of quantum computing. So we've come quantum mechanics and into computing. We've come very far. But from quantum computing perspective, it is Richard Feynman who was trying to replicate the molecular behavior with computer. He soon realized that with the classical computing, it is not possible because of the way the gates and all those sort of things work, which we can cover later. And then he deduced that we need to come up with quantum computing in 1980, which is like my age. It's like 40 years now, and it took us 40 years to come to the stage where we have your NISQ. NISQ is a minimum viable computing product that is available, and you have a D-Wave. A company called D-Wave has developed a quantum computing with 200 qubits. That's the most practical application that is there available in the industry now. I'd like to show you how it looks. So this, can you guys see I hope you guys can see my screen. So this is D-Wave. This is the real world quantum computer. This is the advanced version that is available with us. It's a D-Wave 2000Q. Yeah, QPUs and all those sort of things. So its power is 200 qubits. I'd like you guys now, I hopefully just 5 minutes of this video just to get across the concepts, before just the last video that you guys can see before I move on to the core concepts. This is a good video that I play to most of my audiences. I'll try to see if I can share the audio one more time. Share audio, okay.
Here, inside this refrigerator, at a temperature just a tick above absolute zero, isolated from the rest of the universe, is a quantum computer. If you believe the hype, this nascent technology embodies the promise of the future and has the potential to revolutionize our lives with its turbocharged computation. But quantum computers aren't the next generation of supercomputers. They're something else entirely. And before we can even begin to talk about their potential applications, we need to understand the fundamental physics that drives the theory of quantum computing. We'll need to dive into another dimension, smaller and more alien than anything we intuitively understand: the subatomic world of quantum mechanics. In the 1980s, one of the most important physicists of the 20th century encountered a major roadblock. Richard Feynman was hungry for a window into the quantum universe. But quantum systems, by nature, are fragile, and the information they hold hides from us. Because Feynman couldn't directly observe quantum events, he wanted to design a simulation. It quickly became clear that his computer wasn't up to the task. As he added particles to the quantum systems he was modeling, the cost of computation began to rise exponentially. Feynman concluded that classical computers just can't scale up fast enough to keep pace with the growing complexity of quantum calculations. Then he had a breakthrough. What if he could design a tool made up of quantum elements itself? This instrument would operate according to the laws of quantum physics, making it the perfect way to probe the mysteries of the quantum realm. The idea of the quantum computer was born, and by dreaming it up, Feynman had started to build a bridge between quantum physics and computer science. To understand how quantum computing works, it's essential to start by understanding what makes a quantum in the first place. This means that we need to talk about what's at the heart of quantum physics, a concept called amplitudes.
Quantum mechanics, at its core, is a change to the rules of probability. And this is also where the power of quantum computing comes from these different rules of probability than the ones that we are used to.
For example, if you want to know the classical probability of an event, say a coin landing tails exactly 10 times out of 20, you add up the probabilities of all the different ways that event could happen. That's just common sense. But common sense doesn't govern the quantum universe. Before you measure a subatomic particle, you can think about it as a wave of probability that exists in a kind of black box, a quantum system with many different chances of being in many different places.
Amplitudes are closely related to probabilities, but they're not probabilities. A key difference is, while probability is always a number from 0 to 1. Amplitudes are complex numbers. And what this means is that they obey different rules. If I want to know the total amplitude for something to happen, I have to add up the amplitudes for all the different ways that it could have happened. But when I add up amplitudes, I see something new, which is that a particle might reach a certain place one way with a positive amplitude and another way with a negative amplitude. And if that happens, then those two amplitudes can cancel each other out so that the total amplitude would be 0. And that would mean that that thing would never happen at all. This is sort of the central thing that quantum mechanics says about the world, right? That the way that you describe a physical system is by a list of amplitudes. And the way that a physical system changes over time is by a linear transformation of these amplitudes.
But how can quantum computers use amplitudes to store and manipulate information quantumly? This is a qubit. It's the basic computational unit in quantum computing. Qubits are like bits in a classical computer, but with a crucial difference. A bit is binary. It stores information in strings of binary digits that can only be 0 or 1. But qubits are made of subatomic particles, so they operate according to subatomic logic. Qubits can be 0, 1, or what we call a linear combination of 0 and 1. This fluid combination of amplitudes is at the core of quantum computing. Before you measure a qubit, it exists in a state called superposition. You can think about it as a quantum version of a probability distribution, where each qubit has some amplitude for being 0 and some amplitude for being 1. Superposition is the reason why it takes a vast number of classical bits to describe the quantum state of even a tiny number of particles.
I guess that gives you a bit of an overview. I think we're running short of time. I don't know whether we are still in. Do we have time? Can we continue? I'll quickly run through this.
Yes, sir, you can continue, sir.
Sure. Thanks for that. Sorry, just conscious of the time. So as you can see, this is the the quantum computing history. If you plot it in a number of years, you see 100 years. It took 100 years. We made no progress. That is including 1920 until 2020. I think recently we made some progress in terms of identifying the NISQ computers and the D-wave computer that I showed you guys. We are almost close to the inflection point. Inflection point means something is about to happen. Something that's groundbreaking is about to happen. In quantum computing world, all the use cases that we currently have are all not so much into practical uses. They're all for research purpose. So what is a quantum computing? In essence, what is a quantum computing? So as the picture, that's why I wanted you guys to go through that video. So you can see a quantum computer calculates using the spin properties of subatomic particles, whereas classic computers use the charge properties of subatomic particles. What I mean by that is you can see you have in the classical computers, you have gates and you have bits. And whereas in here, you can see the orange bit, I'm not sure whether I can highlight here, the network of qubits is all you have. You have no gates at all. So the probabilities are endless because In classical computing, you have a limit of 400K gates, and beyond that you cannot go. That's the physical limit of existing classical computing. Whereas with network of qubits, its limit is endless. So that's the classical example of quantum computing and how it's really used. Quantum superposition, I think we can explain a lot of things using this. And this spot sphere is very important for explaining superposition. Superposition is, a misnomer is there. It means it's there everywhere. It exists in, it's a sort of a parallelism, but it's not. So it's not about parallelism. It's about ability for having all possible combinations. So there are three important things to note here. If you look at it, the digital classic logic computing is represented. You have either a 0 or a 1 using those blue dots. The possibilities are just that. Let's say a point at the blue dot at the B is 0 and a blue dot at A is 1. Those are the two probabilities. Let's say fuzzy logic is also part of classical computing, which can apply ranges of values between 0 and 1. But whereas quantum computing can put the dots, the values can be anywhere, as it's as the previous video said, it's amplitude. It can be anywhere. Just to be clear, we'll cover in the subsequent slides. So quantum interference is exactly how a wave, an independent wave affects the other, and it's like when you throw a stone in the water, it creates a ripple effect, and you throw another stone, both those two waves combine and it affects the resulting wave. Exactly how the individual particles interference affects the output. So let's read this, right? Quantum physics tells us that particles have wave properties. So just like radio wave from one broadcast station can interfere with those from another, the trajectory of one subatomic particle, like an electron or a photon, can affect the trajectory of another. So overlapping waves form a superimposed result. I'll show you how it all makes sense at the end. This is all the basic concepts. So quantum entanglement. This is the most discussed and exotic topic of quantum computing and quantum physics and quantum mechanics per se. So I'd like to imagine it like a seesaw, right? A state change in one qubit and an entangled photon. If you have two entangled photons, a state change in one can instantaneously affect the state change in the other. So how I imagine this is like a seesaw. So if one goes down, the other automatically goes up. That's how you imagine entanglement. So we will really see how it is practically implemented in the subsequent slides. But for now, you can imagine it's like a seesaw, right? So one goes up, the other automatically goes down. The distance between the two photons doesn't matter. It automatically changes. This is something called teleportation, but we'll cover that later. Okay, putting analog back into digital. Okay, so this is holistically a single page view of what classical computing or logic gates offer and what quantum logic gates offer. Imagine it's like by virtue itself, quantum computing has got a lot of advantages, and I'd like to compare this with a bird that travels faster than a land animal. Because it flies higher in the sky, it can go faster. It's not its ability, but it's by virtue, because it's a bird, it's able to exhibit different range of motions to get to a target state faster. It's very similar, whereas a land animal, it's got its limitations to use the ground. So that's the difference between a very layman's difference between logic, the classic logic gates and quantum logic gates, or quantum computing, or logical or classical quantum classical computing. So quantum logic gates operate differently from classical logic gates. The concept is, as I previously mentioned, it is not the parallelism. People think all the possible values exist, but it's not the case. It's the idea that all options are being tried at the same time. And this is what makes machine learning a perfect use case for a machine learning model. It can explore all the possible combinations at the same time. Classical computing can be represented by 3 fundamental logic gates and or not. And whereas the quantum logic gates, I think you guys would know already what this is: Hadamard, Toffoli, and Pauli. Pauli is 3-dimensional. That's why you have X, Y, and Z. So what I'm trying to say is, if you imagine that sphere that I showed you before, just like that land animal could never fly and could only meet a bird that lands on the ground. So a bird can meet a land animal only when it comes and reaches the land. Similarly, a classical logical gate could never put a digital bit on the surface of the sphere except in two distinct locations. Those two blue dots that I mentioned, those two blue dots and the line between there, that's where you can plot your digital bits. It's a complex concept to digest, but that's the beauty of quantum computing. The more you read, the more better you get at it. Right. So this is the quantum computing architecture. What it takes to incorporate this quantum, instead of logical, your logic gates, and instead of removing all these, how do you put qubits and network of qubits into an architecture, an ecosystem that is so used to your CPUs, your GPUs, and all those type of classical computing models. So this is how we split it. The most important thing for us to note is the function bit in the middle. So key functions, key quantum functions are sensing, storing, processing, actuating, transmitting. We would cover this in the subsequent slides, but to your knowledge, just understand these. So just grasp this slide. This is the foundation. So this is all it takes to deliver a quantum computing. You need an ecosystem, like you need investment, you need someone to support you, and you need a proper constructs in place for you to commercially engage others. Also, you need architectures in place, like your algorithms need to be in a position. Your classical neural network needs to be converted into your quantum neural network. So a quantum AI is completely, or it's got a different flavor to classical AI. So the algorithms, the protocols is the way these algorithms communicate with each other. Those are protocols. Your for example, your HTTP, your TLS, and all these other things are your protocols. And models is again your machine learning model. And function is the is the centerpiece where all the action happens, where all the manipulation of photons or all these things happen. Sorry, what? So the application again is a control, communication, computation parameters, and then the hardware, the firmware, and the software. These are the things that are built around the quantum computing that it takes for you to make quantum computing pragmatic, for you to achieve all this. Right now, it's all conceptual, it's all isolated. For it to work as like for a common citizen, for you, for a quantum computer to reach you, you need these type of parameters. I'll only cover the quantum function. I'll tell you what quantum function is all about quickly. So sensing function within a quantum function, it is the ability to measure or detect some occurrences, right? The sensing function is, if you ask me, the maturity at the stage is medium to high readiness. It's there in the industry. People are looking to leverage this concept. So SQUID or a superconducting quantum interference device consists of two superconducting coils connected via an insulator that allows flow of electrons in each coil to be entangled at a low temperature. So the electrons and electrons are very, very sensitive to the environment. So that's why you see any supercomputer, it's kept in a cold place. It's very protected. It's got a lot of protection around it. So the real use case is the coils measure minute changes in magnetic fields. Therefore, for diseases like Alzheimer's, brain waves and brain patterns are very important in understanding diseases like Alzheimer's. So this is making a lot of breakthrough in that industry. And there's a lot of learning that people are making through this particular use case. Tristan Technologies manufactures, you can Google this up, they manufactured encephalography equipment for commercial use. So this is what is used through quantum computing, through quantum logic. They have invented this machine to identify brain waves, the minute of brain patterns that are there in our human brains to solve problems like Alzheimer. And then there is another company, or there is another University of Bordeaux in France. They have invented something called Gravimetry, which identifies minute variations in gravitational fields using the same SQUID device or the concept. So it's a gravimeter. The gravimeter is the size of a small computer at your desk. But what it does is it uses system of laser to trap and pull atoms down to few millikelvins, and observes the changes in the vertical acceleration again using lasers. So it changes, it pulls it down and observes how the photons change. And then storing is one of the key quantum function. So leading method in storing quantum information is quantum repeaters. This is used again in cryptographic, key, the shards and the cryptographics and the Fourier transform and all those sort of things. So quantum, you guys should Google this. Quantum repeaters is used for storing any state change. For example, it is used to store quantum information such as the second entangled pair of photons that may transmit it along. Well, I'll show you in the next subsequent slides how teleportation happens using this particular concept of storing. So this is NISC processing. So processing is basically your compute power. So you see, as you can see in quantum computing, you go through a lot of stages. See, you have to sense a change first of all. So you need sensors and devices to identify a quantum, any change in quantum realm or the photons or the electrons, and you need to store the change. And once it's stored, you need to transmit and you need to process that information for you to infer any value. So this is the basis. So we are in the processing stage where we are in the medium to low readiness. The market is ready, and it's invented a lot of computers using different types of computers using NISC, which is a minimum viable computing that is available for the market. Actuating is actually the output. Once you get the result, it's the surfacing layer. This is nothing to do with quantum, but it is very key in surfacing all the values or the results, or for example, as an example, a system of amplifiers that would use to control a display panel, and this is more like a display panel. Quantum function. So this is the last of the quantum function, transmitting. This is a very confusing topic, but this is what enables teleportation. So anyone tells you using quantum methodologies, we transmit people as well. At one point in time, you can do time travel or something like that. This is that logic that they talk about. I'll try to explain to the best of my ability. Let's say you have communication station A, it's a sender, and you have communication station B, which is the receiver. I'll read this out first before I explain. Station A is the sender that can control what the station B sees, namely the state of photon P4. So there's P1, there's P4. We're going to transmit system from P1 to P4. So how that happens is through, I'll tell you the technique. So what happens is, what we're going to do is we're going to change the state of P4 by affecting the state of P1. This is as a result of a measurement made in the third location, which superimposes the states of P2 onto P3, which then affects the state of P4. So that's where, this is like, since P2 and P3 were originally entangled with P1 and P4 respectively, the superposition of P2, P3 makes both P1, P4 take on the complementary state of P2 and P3. So I'll share this slide with you. You guys read through this. You guys need to digest this state. So what happens is when P1 and P4 therefore takes the state of P1, whereby P1 is destroyed. So P1 gets destroyed at the end. So your copy is sent across to the other side, but the original copy gets destroyed. So you're basically teleported through this transition of different states between two pairs of entangled photons. So that's pretty much the hard bit. But what will be the impact of quantum computing in the real world? It's mostly right now what's happening is in the molecular biology, microbiology, synthetic biology. It's making a lot of breakthrough because it's more aligned to the molecular level investigations that they do is more aligned to quantum realm. And in real world situations like the Shor algorithm, the internet that we use uses certificates, public keys and private keys to exchange information, safely transfer information. But with GPUs and all these sort of things, we are at the verge of breaking through the Shor algorithm. But with quantum computing, We can have, highly robust encryption technologies that would protect us from, getting hacked or, getting hijacked, your ransomwares and all those sort of things. And then there's a massive machine learning use cases that are lined up. For example, entangled qubits, like the previous example, entangled qubits acts like a node in neural networks. So those neural networks, these qubits, if they're entangled, the phase change of each other, the photons would affect each other, and it would recognize multiple patterns in the same neuromorphic computer architecture. Remember, we were trying to establish an animal behavior pattern in computer models. Similarly, we're trying to those kind of use cases are possible using entangled qubits. And massive and network topologies offer massive parallelism via high degree of internodal interaction. There will be a lot of communication, and there will be a lot of data points that you can capture because there's simply a lot of place you can store. A qubit offers you more storage space compared to bit. And better biotechnology, chemical processes, at an atomic level, you can do modeling. This requires modeling electron spins, which is a complex undertaking when considering the aggregate interaction between various atoms of the interacting molecules. This is very difficult using a conventional computing, but quantum computing makes this possible. So what we can do, so for you guys to start, I'll give you, some examples where you can start. These are all the complex use cases that there is. I have a very interesting small short 3-minute video. I'm not sure that the time allows us to do that, but it will really be beneficial for the students. Can I go ahead and share a 2-minute video?
You can share, sir.
Thank you. No. This is IBM's quantum computing, where the vendors are going. So key to staying ahead of the market is you need to understand where the market is going. So IBM has been doing a lot of research. I'd like to show you guys this future of electric cars, which will be soon coming to India. And thereby you would have an ecosystem.
Mercedes-Benz has been moving people and goods around the planet for over 130 years now. Every day we ask ourselves, how can we bring the future into reality? This is at the heart of who we are, and this can only be achieved by continuously innovating. Right now, our industry is in a transition to a new age. It's time to reduce our impact on the planet. Our goal is for the entire Mercedes-Benz vehicle fleet to be carbon neutral by 2039. That means implementing electric driving in all divisions as a priority. For that, we need to focus on next-generation battery technology.
The thing that has always held battery technology back, and this will sound strange, is that we don't really know what goes on inside of batteries. This thing is a mystery. Sure, we know how to make batteries, but we can't actually see what's happening at a molecular level inside the battery while it's working. A battery is more like a complex ecosystem than a machine that spits out electricity. It's chaos in there. And to make things even harder, there isn't a supercomputer on the planet right now that could accurately simulate what's going on in there either. Simulating this at the molecular level, accounting for a tremendous number of electron interactions, each electron influencing the other in complex ways. Accurately simulating electron interactions in the simplest molecules takes many days on the most powerful supercomputers on the planet. And as for the reactions in a battery, forget it. So what we approximate the chemical reactions in a battery using classical algorithms. They're not very good and average out a lot of reactions and make a lot of assumptions, but they're all we have. So designing more efficient batteries is a laborious process of trial and error that takes decades.
Mercedes-Benz has turned to IBM Quantum to explore how we can simulate the chemical reactions in batteries more accurately. IBM quantum computers are built with quantum mechanical systems at their heart. They are designed to simulate quantum systems such as chemical reactions far more efficiently than classical supercomputers. With these simulations, we're exploring new materials to create more efficient batteries. At Mercedes-Benz, we continue to advance our development of current and future high-performance lithium-ion batteries, but also have a close look at what's beyond lithium-ion. We strive to explore cutting-edge technologies for our customers in support of the high-volume electrification.
So that's one of the real-world use cases where the world is going. So they are starting to use these type of, they're starting to use quantum computing to explore these type of use cases. Can you guys see my screen? Can everyone see my screen?
Yes, sir.
Okay, sorry. Okay. So this is what you guys can do as a student, right? First year into engineering, computer science engineering. There are a lot of cloud vendors that offer quantum computing for you guys to test it out, trial it, build your own algorithm, just an algorithm to just detect something, some sort of a just detect some letters or numbers or something like that. You build something like that and then run it through Amazon Bracket. So Amazon Bracket is Amazon's version of quantum computing. It is free. You can trial it. All you need to do is set up an account, and then with a range of other services that they offer. Amazon Bracket is also available for you to trial. But when you trial this, after you finish the trial, make sure you delete the instance. That's what you need to make sure, otherwise you keep getting the bill. So watch out when you use this, you got to be careful. So these are the jobs in the future that that's going to the top jobs in 2035 that you're going to have. So we need to focus on. So you guys are upcoming engineers. You guys are looking at Java developer, .NET developer. But look, these are the jobs that's going to trend in the next 10 years. The virtual store Sherpa, personal data broker, personal memory curator, augmented reality journey builder, body part maker. This is all possible with the nanotechnology and the quantum computing. And the memory augmentation surgeon to boost your memory, patient's memory with Alzheimer's, blah, blah, blah. So all those sort of things. So the world is changing. When I started my career as well, there was nothing called a DevOps. Now DevOps is everywhere. So everybody is using DevOps. So these are the technologies that you guys should keep your eyes open and start on the side, do your own learning to get better and to be better equipped when you go out to the market. These are the technology trends that I noticed that I thought I'd share with you guys from AI perspective and from quantum perspective. As you can see, there's applied AI that is there. Number one is the next level of process automation. So process automation comes, a quantum computer powers a lot of next level process automation. Process automation is anything that a mundane task that a human does, you can completely automate that. That is what is called process automation. So these are the top industry trends, that's likely to trend in the next 10 years. So these are my resources. You can go into Azure quantum computing. They have a fair bit of knowledge and they have a fair bit of playground for you guys to trial out quantum computing. There's Google AI computing as well. I'm trying to be very vendor neutral. That's why I'm just pick one from Google, pick one from Azure, pick one from Amazon. They all offer similar sort of capabilities. You guys need to go in and explore when you're free. I'd like to wrap the session up with this quote, my favorite quote: live as if you were to die tomorrow, learn as if you were to live forever. This is what Mahatma Gandhi quoted. So you got to have that inquisitive brain for you to learn. You need to have that continuous learning mindset, and knowledge would pay you benefit one day. You won't see the benefit right away, but as you accumulate your knowledge, one day you will see how well-rounded you are. A good teacher can inspire hope, ignite the imagination, and instill a love of learning. That's by Brad Henry. I guess from your management perspective, from your college perspective, I think they are, at my university did not offer me this, sort of exposure, but I guess you guys are lucky. You guys have, your good teachers. You guys are in the right hand. They are offering you this level of exposure, at this, juncture in your life. So I really like to thank you, and I hand it, I'd like to thank, the HOD of CAC department, and also Savita ma'am and Sangeeta ma'am for this amazing opportunity. Hope I, brought you guys some level of understanding of the existing real world complexities about AI and quantum computing. I now hand it over to Sangeeta ma'am.
Yeah, thank you, sir. Thank you for the wonderful presentation. I am Priya here. Okay, so students, if you have any doubts, you can ask now. I think you can unmute yourself and talk. The session is open for discussion.
If you guys are shy, you guys can chat as well. I can answer in chat. Or you can send, I'll share my email address here. I'll share my email address and you guys can feel free to as well. For people who cannot ask here, you can ask me directly. I'll share my email address with Sangeeta ma'am, and Sangeeta ma'am can definitely pass the questions and I can answer. I think it's me standing between you and your lunch. If you guys don't have any questions, you can always reach me through Sangeeta ma'am.
Yeah, thank you, sir. I think they will be sending the questions to ma'am, and we can in chat. Let me check. Yeah, the feedback link is given in the chat, and you can put your feedback there. And if you have any questions, you can post it in the chat box as well. Or you can discuss with your faculty so that it will be known to the known to Sangeeta ma'am also.
Thank you, Hari.
Yeah, thank you, sir. It's given. Okay, so I thank you for your wonderful presentation, sir. It was an eye-opener to every one of us, for the faculty as well, because we can learn how it is identified, and how the numbers are identified, how one can search the car and everything. Okay, so you started from there, and what are the work, that is the job availabilities in the future. And thank you so much for your wonderful presentation. I think students might have learned a lot from this. And if any student can give the feedback also. Any student is willing to give the feedback of this? Okay, I think they will be putting it in the chat box. So thank you so much.
You guys are a shy mob, I gotta tell you that. You guys.
My dear children, you can put your feedback also, or if you have any doubt.
That's fine.
Yeah. Okay, sir. I think they will be putting it in their mind, and the doubts will be coming later. Okay.
No problem. That's all right. I'm always here to assist, and thank you all for the opportunity, and thank you guys for taking some time to listen to my, I wouldn't say a lecture, my experience. I thought I'd share my experience, and I tried to keep it as simple as possible. Yeah. And I hope I've driven some knowledge into your young brains.
Yes, sir. Sure, sir. Sure, sir. It is a lot of knowledge, and I would like to thank the management and principal for giving this opportunity to conduct the session. I would like to thank Sangeeta ma'am for arranging this meeting, and I would like to thank Mr. Rajesh Bhaskaran for this wonderful presentation. And I thank everyone in the department for conducting this meeting as a successful one. Thank you, sir. Thank you so much. Thank you, my dear children. You can go to the feedback link and put the feedback.
Thank you. I'll now drop off. Thank you, guys.
Thank you, sir. Thank you.